Welcome to our deep dive into buffer bloat, a subtle yet pervasive issue impacting network performance, particularly in ultra-scalable systems. While often overlooked, buffer bloat can silently degrade your network's responsiveness, transforming what appears to be ample bandwidth into a frustratingly laggy experience. Today, we'll peel back the layers to understand this phenomenon, its causes, its profound impact on latency and throughput, and most importantly, how we can effectively combat it to build more resilient and responsive network architectures. This isn't just a theoretical problem, it's a critical challenge for anyone designing or operating modern high-performance systems, where user experience and real-time interactions are paramount. Get ready to rethink how you perceive network queues and buffer management. At its core, buffer bloat refers to the excessive buffering of packets in network devices, such as routers, switches, and even operating system network stacks. While buffers are essential to absorb traffic bursts and prevent packet loss during temporary congestion, overly large or poorly managed buffers can lead to a phenomenon where queues grow excessively long, causing packets to spend unnecessary time waiting to be transmitted. This waiting time directly translates into increased latency, even when there's available bandwidth. Imagine a highway with too many lanes leading to a single toll booth. Cars might not be crashing, but everyone is stuck in a long, slow-moving line. That's buffer bloat, congestion that manifests as latency rather than outright packet drops. Throughput trade-off. Traditionally, larger buffers were seen as beneficial for achieving higher throughput. By holding more packets, a router could keep its transmission link busy for longer, thus maximizing bandwidth utilization and throughput, especially under bursty traffic conditions. However, this comes at a significant cost: latency. Every packet stored in an oversized buffer contributes to increased queuing delay. A small buffer might drop packets under heavy load, reducing throughput but keeping latency low. A large buffer might never drop a packet, ensuring high throughput, but at the expense of adding hundreds of milliseconds or even seconds of delay. The challenge for scalable systems is to find that optimal Goldilocks zone, enough buffer to handle bursts without introducing detrimental latency. Buffer bloat isn't just a random occurrence. It stems from several interconnected factors. One primary cause is the always fill the pipe mentality of TCP congestion algorithms. Traditional TCP implementations are designed to aggressively send data until packet loss is detected, indicating network congestion. With large buffers, it takes much longer for these buffers to fill up and for packet loss to occur, effectively masking congestion and allowing queues to grow before TCP backs off. Another factor is overly generous buffer sizing by device manufacturers, often to prevent packet loss under stress tests, but without considering latency implications. Lastly, heterogeneous network speeds can contribute. Imagine a fast Wi-Fi network feeding into a slower DSL line. The faster network can quickly overwhelm the slower link's buffer. The consequences of buffer bloat are far-reaching, particularly for user experience and the reliability of scalable systems. For users, it manifests as frustrating lag during video calls, stuttering in online gaming, delayed web page loads, and general sluggishness in interactive applications. Even with high bandwidth, responsiveness suffers. In scalable systems where microservices communicate or distributed databases synchronize, buffer bloat can introduce significant delays, impacting transaction commit times, increasing the likelihood of timeouts, and causing cascading failures. It can disrupt real-time analytics, make IoT device communication unreliable, and generally undermine the performance guarantees of modern applications. A system might be designed for high throughput, but if latency is high, it's not truly performing as expected. Historically, network administrators have attempted to mitigate congestion with various strategies, but many fall short when addressing buffer bloat directly. Simply increasing bandwidth often just postpones the problem. A fatter pipe can still have an overly large buffer at its endpoint, simply moving more packets into the slow queue. QoS, or quality of service, attempts to prioritize certain traffic types, which can help critical applications, but it doesn't solve the underlying issue of inflated buffers for the non-prioritized traffic or overall network health. And while static buffer sizing might seem like a solution, it's notoriously difficult to get right. What's optimal for one network condition might be detrimental for another. These approaches often act as band-aids, managing symptoms rather than curing the root cause of excessive queuing delay. Enter Active Queue Management, or AQM, a paradigm shift in how we manage network queues. Unlike traditional passive queue management, where packets are only dropped when the buffer is completely full, AQM algorithms actively monitor queue lengths and provide early congestion signals. By dropping or marking packets before the buffer is entirely saturated, AQM prompts senders, like TCP flows, to slow down earlier, preventing buffers from filling up excessively. This proactive approach helps maintain shorter average queue lengths, significantly reducing queuing latency while preserving good throughput. It's like having a smart traffic controller that starts signaling slowdowns as traffic builds up, rather than waiting for gridlock. AQM is a fundamental component for addressing buffer bloat effectively. While the concept of AQM has been around for some time, its practical adoption and effectiveness have soared with algorithms like CODEL, controlled delay, and FQ-CODEL, fair queuing, controlled delay. CODEL is particularly innovative because it focuses on maintaining low queuing delay by monitoring the time a packet spends in the queue, rather than just the queue length. If a packet's sojourn time exceeds a predefined target, e.g. 5 milliseconds, CODEL begins dropping packets until the delay is brought back under control. FQ-CODEL builds upon this by adding fair queuing, which isolates different traffic flows from each other, preventing a single aggressive flow from hogging the buffer and causing delay for others. These algorithms are now widely adopted in Linux kernels and various network equipment, making AQM a real-world solution. While AQM is a powerful weapon against buffer bloat, a truly holistic approach involves other strategies. End-host tuning, such as optimizing TCP buffer sizes on servers and clients, can prevent unnecessary buffering at the edges of the network. Application layer pacing can also help, ensuring applications send data at a rate that the network can sustain without overwhelming buffers. Furthermore, as networks evolve, emerging technologies like QUIC, with its stream-based multiplexing and improved congestion control, offer new avenues for reducing latency and improving responsiveness. The future of combating buffer bloat lies not just in better queue management, but in a synergistic approach that spans hardware, operating systems, and application design, continually adapting to dynamic network conditions. In conclusion, buffer bloat is more than just a minor inconvenience. It's a critical challenge for building high-performance, ultra-scalable systems. It subtly undermines the benefits of increased bandwidth by introducing insidious latency, directly impacting user experience and system reliability. We've explored its causes, its profound impact, and the limitations of traditional fixes. Crucially, we've seen how active queue management, particularly through implementations like CODEL and FQ-CODEL, offers a robust, proactive solution. By understanding the latency throughput trade-off and adopting a holistic strategy that combines AQM with end-host tuning and application-aware design, we can master the buffer bloat challenge. The goal is clear: responsive, low-latency networks that truly deliver on the promise of modern technology.